Welcome everybody to calculus class online. We'll get started in a minute. If you want to follow with the notes, they're on Blackboard. We're going to cover polar coordinates today, introduction to polar coordinates, and I'll make a small homework assignment that will be due tonight after you watch the video, just to test that you understand the basic concepts. Alright, so let's get started. So we're looking at a different way to graph functions and to think about coordinates. As you know, we usually have the xy coordinate system, rectangular, and that's x versus y. And then when you have a point here, like 2, 3, that means that your distance from the y-axis is 2, and the distance from the x-axis is 3. So I didn't really draw that to scale. All right. So instead of thinking about rectangles, because you basically get rectangles when you draw a point, let's think more in terms of angles and distances. So let a point P be in the plane. It can be represented by polar coordinates r theta. So instead of xy, like in this case we have xy, in this case we'll have r theta. What is r? So here's our point P, and r is the distance from the origin to the point, like basically the length of this line segment, and theta is the angle from the positive x-axis. So you always measure it from the positive x-axis, counterclockwise. So you travel counterclockwise. This is called the polar axis here, and the origin 0, 0. In this case, it's called the pole. It's the center. All right. So, for example, if r theta equals 2 pi over 4, then what we're thinking of, and basically the xy coordinate system and the polar coordinate system, they both can give you the same picture. You can talk about both of them simultaneously. So you still have the y-axis and the x-axis, but we're just referring to the point with a different name, a different system. Okay, so first you find the angle. Here's pi over 4, that's 45 degrees. And then you travel out a distance 2. So from here to here would be a distance 2, and then this angle would be pi over 4, 45 degrees. So basically travel at 45 degrees a distance 2, and that's how you get to the point 2 comma pi over 4 in polar coordinates. All right, now there is of course an easy way to convert back and forth between polar coordinates and rectangular coordinates, or Cartesian is the technical word, and use this formula here. You've probably seen this in physics whenever you dealt with vectors. Whenever you dealt with vectors in angle form, angle magnitude form, and then when you went to component form. It's basically the same idea. All right, so x is r cosine theta, y is r sine of theta. That follows from simple trigonometry, r cosine theta, r sine theta, just using the definition of sine and cosine. So that will give you the x, y coordinates of that point. And if you want to go the other way, well, the Pythagorean theorem. So this would be x and y here. So the Pythagorean theorem would give you r. And to get the angle, you have to use the tangent. But the tangent, so the tangent of theta would be y over x. So solving for theta, you use the arctangent. And you have to adjust the quadrant. So what that means is the possible answer for theta could be anywhere from 0 degrees, 0 radians, to 360 degrees, 2 pi radians. So you do have to get the correct quadrant right. You might have to adjust the angle. Arctangent typically only gives you certain angles. It gives you the angles. So here's the tangent. It only goes from pi over 2 to negative pi over 2. So if you need an angle outside of that range, see that would be this range. It would be from here, negative pi over 2, to up here, positive pi over 2. Negative pi over 2, positive pi over 2. So you might need to add pi to go from like here to here, or to go from here to here to get the right angle. We'll see some examples. All right, so our first example is to try to convert 4 pi over 3 from polar to Cartesian. All right, so we're in polar and we want to go to Cartesian. That's easy. That's the easiest way. You go directly to these two formulas here. R is 4, and the angle is pi over 3. Make sure, as usual, that you're in radians. Make sure you're in radians. And plugging into the formula, we get our x and y value. And it's the point 2 comma 2 radical 3. All right. Let's convert a rectangular negative 3 comma 3 from Cartesian to polar. See, sometimes when you just see an ordered pair, it's not so easy to tell whether you're in Cartesian or polar. You sort of have to be given that information. They have to tell you r theta, or at least they have to say this is polar, because you can't really tell from here and here. You could be in, this could be Cartesian and that could be polar. It's not, but you have to be given that information. All right, let's see. Convert negative 3 3 from Cartesian to polar. So what are we going to do? X and y. So that's x and that's y. So for this problem, x is negative 3 and x is negative 3 and y is 3. And going to the Pythagorean theorem, that'll get us r immediately. No trouble there. And let's see about the angle. How do we find the angle, right? So we have to say inverse tangent, arctangent, inverse tangent of y over x. 3 over negative 3. So what's the angle whose tangent is minus 1? The tangent is 1 at 45 degrees, so it's negative 45, negative pi over 4. But is that the right quadrant? So that's the million-dollar question, right? Is that the right quadrant? So let's see. So for what you do is you have to graph the point. X equals negative 3, y equals 3. It's a little confusing, so we keep going back and forth between rectangular and polar here. So negative 3, 3. So let's say we're right here. Negative pi over 4 as an angle is not correct, see? You know, this angle here, this is negative pi over 4. So what we need to do is shift the arctangent by its period. Its period is pi. So t is the period, it's pi. So if we shift it by pi, what we'll end up doing is we'll go from negative 45 degrees to 180 minus 45, and this would be 45 here, 135. So 3 pi over 4. All right, so we get negative pi over 4 from the calculator, but to get it into quadrant 2, right, quadrant 2 is over here, we need to add pi to the negative pi over 4 that we got, and we get 3 pi over 4. Remember this fact about the tangent. The tangent of pi plus theta is equal to the tangent of theta for any value of theta. That's because the period of the tangent is pi. It repeats itself every pi. So if this is an answer for the arctangent, this always has to also be an answer for the arctangent. You're guaranteed that. Okay. Convert. Here's one for you to try yourself. Convert 60 and 5 pi over 2 from polar to Cartesian. So you are given that these are in polar. 60 is a polar and 5 pi over 2 is polar. See if you can convert these to Cartesian. That should be easy, right? You're just basically using this formula over there. All right. And another quick example, you can pause the video if you like and try it out. Convert 0, negative 4, and 3, 3 from Cartesian to polar. All right, and check your answer. Answer is 4, 3 pi over 2, and 3 radical 2 pi over 4. Pretty similar to the one we just did before. This one's a little easier because the quadrant is 1. When the quadrant's 1, if the quadrant's 1 or 4, the arctangent will give you the answer right away. You won't have to shift it. Here, x equals 0, y equals minus 4. That quadrant, that's on the border of quadrant 3 and 4. So you should get a correct answer. They chose to do 3 pi over 2. You could have also done negative pi over 2. That would have been a correct answer too. There's actually, this is an important point, there's multiple ways to label a point in polar coordinates. So what do I mean by that? So let's say this is our point. See, R is 4, theta, negative pi over 2. Right, so that's one way to label it, like this. But you could also label it by going counterclockwise, as I originally said. So if you go counterclockwise, the angle gets bigger and positive. So another way is to say this is 4, 3 pi over 2, 270 degrees. So they're equal to each other. They give you the same point on the xy plane. They basically reference the same point. but as you could see, they do look different. So this happens quite a lot in polar coordinates. All right. The next thing we're going to look at is, and this is a bit more complicated, is how to graph a polar function. So there's some useful guidelines here on page 3, and I think it's best if we come back to this, that we start with an example and then come back to this and maybe as more like a reference. So let's skip the page and look at our first example. All right, so we want to graph r equals 2 plus 1 cosine of theta. So the first thing that you should keep in mind is that instead of y equals f of x, like we're used to, hold on, I'll be right back. All right, so normally when we graph, y is equal to f of x, right? So y equals f of x is the normal way of graphing a Cartesian equation. We all know this. We've seen this basically forever. Okay, what's new is r equals a function of theta. So all it's telling us is there's some kind of relationship between theta and r. You plug in a value for theta, and we get a value for r. And then we plot those points. It's basically going to be a one-dimensional graph because theta will vary in one dimension. If you didn't have an equation for r and theta, then every point could possibly be, you wouldn't have a graph, you basically have every point. So in order to get a nice graph, it needs to be one-dimensional. So the parameter is theta. All right, so let's see how this works. So let's go right to the table values. We'll come back to some of this other stuff soon. So the equation that we're going to look at is r equals 2 times 1 plus cosine theta. So this is the function. We plug in a value for theta, and we get a value for r. And that's how we get our ordered pair. And remembering that we're in polar coordinates, we just have to graph r comma theta. Okay. Theta. Let's plug in some values for theta. 0, pi over 3, pi over 2, 2 pi over 3 pi, 4 pi over 3, 3 pi over 2. If you put them in degrees, you're basically looking at 30, 60, 90, 20, up to like 300, and 270 is 3 pi over 2. So looks like we have a few more points here, but let's see. Oh no, 300? No, they don't have 300 here, but you could easily calculate it. Okay, so let's see what's happening. All right, theta is 0, cosine of 0 is 1. So going to the formula, 2 times 1 plus cosine theta, r is 4. All right, so basically if you use this formula and you plug in theta equals 0, you'll get r equals 4. 2 times 2. All right, when theta is pi over, so let's see that point. Angle 0, r is 4. So far it checks out, and that's the dot we're thinking of. That's the point. Pi over 3, that would be 60 degrees. So we're right here on this line here. And if you plug in theta, the value for r is 3. So let's see. 1, 2, 3. So this is the point. See right here, this is the point. R equals 3. Theta equals pi over 3. This is a nice way to graph because we have the nice sectors here. Instead of squares and rectangles, we have sectors. So this is the more natural way to graph a polar function, polar coordinate function. All right, let's see. Pi over 2, r is 2. See, here we are. Pi over 2, 2 comma pi over 2. That's that point right there. 2 pi over 3, r is 1, right there. Pi, this is pi here. R is 0. Okay, we're at the pole. Pole is the origin. 4 pi over 3. Right here, r is 1. So we start here and we go 1 along this angle. And then the last one, 3 pi over 2. That's this ray. 2 is r. So 2 comma 3 pi over 2. And then even though it's not on the table, it looks like they do one more point here, 300 degrees. All right, so you connect the dots. We basically start here and we go in this direction. And we come in a little bit, and then a little cusp there, come back, and we complete this figure. It's called a cardioid, and notice cosine is periodic. Period is 2 pi, right? That means cosine of 2 pi plus theta equals the cosine of theta for any value of theta, which means it in particular it'll repeat itself. See, cosine of 2 pi equals cosine of 0. So, and not only will it repeat itself at 0 and 2 pi, it'll retrace itself if you keep on adding 2 pi to the angle. So it wouldn't make sense to let theta go any bigger than 2 pi because it'll just retrace the same picture again. All right, so it completes one full trace from 0 to 2 pi. All right, let's take a look at another graph. This one we'll go through a little faster. R equals 3 sine of 2 theta. All right, give that a try yourself. Why don't you take a minute and see if you can maybe use this as a guide. Make a little table of values. And try to see if you can get an idea for what the graph looks like. All right, so here's the table of values. And you get quite an interesting looking graph. Why does it do this? Well, it basically, when theta is 0, r is 0, so you start at the pole, and you notice by the time you get to pi over 2, you're back to 0 again. So you've basically traced this first petal here. So notice the tangent line. The vertical tangent line would be at the y-axis here, which would correspond to the ray at pi over 2. And then when you continue on, 3 pi over 4, so that would be 135 degrees. In that case, r is actually negative, right? So this is a little unintuitive. When r is negative, instead of going this way, so look, here's 135, 3 pi over 4. So instead of going this way, that would be if r were positive. Since r is negative, you actually go opposite. You go this way. And what you're really getting is this point right here. So this point would correspond to r would be negative 3, and the angle would be 3 pi over 4. So if this was 3 pi over 4, then the that would be the right point. But this point occurs later on. It's a little, as I said, it's unintuitive. See here, it's 7 pi over 4. That would be this angle. So 0, 2 pi, pi, 3 pi over 2, 7 pi over 4. But instead of going this way at that angle, since it's a negative r, you actually go back this way. So this is, as I said, it's a little confusing. You know, it's best to try to avoid negative values of r, but sometimes you can't. All right, so let's take a look at some of these guidelines. Maybe they'll help us get the graph a little bit better. Maybe give us a few shortcuts for finding these graphs. All right, so here's some guidelines. R equals a, or r equals a cosine theta, or r equals a sine theta, they actually give you a circle. We'll see some examples of that. Cardioid, we've done this. A limicot, we'll see if there's a picture for that. Rose spiral. All right, check for symmetry. If you can replace theta with negative theta and the equation is unchanged, then the graph will be symmetric about the x-axis. If you replace theta by pi minus theta and the equation is unchanged, it's symmetric about the y-axis. If you replace r by minus r, or theta by theta plus pi, if it remains unchanged, then you get some symmetry about the origin. So these symmetries are useful. Maybe you don't have to trace the entire graph. Perhaps you can just trace part of it, and the symmetry will help you sort of fill in the missing parts. Find the key points. I think we know this already. Plug in the nice simple angles. Find where r is 0. That's where the curve passes through the origin. Find the max and minimum values of r. Oh, you'd have to maximize a calculus function in theta and see what the biggest and smallest values of r is. All right, create a table of values. We've done that. Plot the points and connect smoothly. Determine the range of theta. Most curves complete in 0 to 2 pi, but some complete a little earlier. All right, let's see if there's what else we have. So just to show you some interesting, r equals 1 plus 2 cosine of theta. If you graph this, you could always fall back on the table of values. And if you plot the points, you get this nice graph. Circle, r equals 4 cosine of theta. So make a table of values. And what you get in this case is a circle that completes from negative pi over 2 to pi over 2, or 0 to pi. So it doesn't need a full 2 pi in order to do the whole circle. And the circle stays in one quadrant. Right? The easiest way to get a circle is just to say r equals 3, or r equals a value. That means theta is not even in the equation. You see, the way that polar coordinates are set up is that straight, like horizontal lines and vertical lines, like in the xy plane, in Cartesian, what is the easiest kind of equation? Like y equals 5, x equals 3. Right? You get vertical, horizontal lines. In polar, if you say r equals r equals 3, then you get all the points that are distance 3 from the pole, from the origin. And that is, by definition, a circle. So what I'm trying to explain is that the simplest way to represent circles is to use polar coordinates. They have the simplest equation. Just like lines have very simple equations in Cartesian. All right, let's take a look at the 3-petaled rose. All right. All right, so area. How do you find area in polar coordinates? That's mostly what the polar coordinates are used for in calculus, is to do integrals. Whenever you have an integral that has circular symmetry, it might very well be the case that polar coordinates would make the integral much easier. So the formula for area is 1/2 r squared d theta. This is dA. So what this basically is giving us is the area of a sector with a small angle d theta, and the radius of the sector is r. So this comes from the area of a sector formula. And instead of using rectangles to calculate area as a Riemann sum, what you instead use is sectors. So it's using sectors, it's like the area of a rectangle is just delta x times f of x, right? The y value times the base, delta x times f of x. So instead of splitting up your region into little rectangles as you would in Cartesian, what you do now is you split it up into little sectors. So imagine a whole bunch of sectors, and using this formula on each sector and integrating them together. So basically, the key formula is right here. Area in polar coordinates, 1/2 r squared d theta. The integral from alpha to beta. Alpha is the starting angle, and beta would be the finishing angle. All right, so I think we're running out of time. Let me see if I can just show you a quick example, and we'll come back to this in class. We'll do this in class more carefully. Find the area enclosed by r equals 4 sine of theta. All right, so the picture is this little circle here, circle of radius 4 that's in quadrants 1 and 2. So basically, your first step would be to graph this equation. R equals 4 sine of theta. Give yourself a little table, plot the points, and you'll see that how to trace the circle. Limits are from 0 to pi. So when theta is 0, you get r equals 0. When theta is pi, so if you start making the table, theta versus r, right? Okay, so start at 0. Sine of 0 is 0. 4 times 0 is 0. R is 0. All right, we're right there. We're at this point. And then you're going to have pi over 4, pi over 2, 3 pi over 4, pi. Just a few points. We need sine of pi, 0. So basically what that means is, and you notice the sign is always positive on this domain, right? The sign, if you remember the graph of the sign, here's pi. See, 0, 0. So we're going. The r will be positive. So the angle is positive, and r is positive. So that's why we stay above the x-axis here. All right. So turns out it's exactly a circle, as we said. And to do the integral, we go from 0 to pi. The 1/2 is part of the formula, right? So the formula is 1/2 the integral of r squared d theta from alpha to beta. Alpha is the start angle, beta is the terminal angle, 0 to pi, and r is the equation right here. R is 4 sine of theta. So 1/2 4 sine of theta quantity squared. Simplify it. We know how to do this integral. We've seen it many times. Use the identity to get rid of the square, the half angle identity. All right, simple u sub. 8 over 2 is 4. Do a simple u sub here. Remember, a 2 will come out under the bottom. U is 2 theta. Du is 2 d theta. All right, just a quick tiny review. U is 2 theta. Du is 2 d theta. Okay. And doing the integral, plugging in theta, pi, plugging in 0, subtracting, answer 4 pi. So yes, this is a circle of radius 2. So the area really is 4 pi. How do you know the area? How do you know it really is a circle of radius 2? Well, that requires a little bit of conversion. You can actually convert this to a rectangular equation. I'm not sure we're going to have time to cover that aspect exactly, but it can be done. It's not hard to convert this to a Cartesian equation using the conversions like we learned in the beginning. All right, so let's stop here. So I'll make a small homework that you can finish up. Should easily be able to finish up if you watch the video, and you could do that homework tonight, please. All right, stay safe, everybody, and I'll see you guys all soon on Wednesday.